All right. So the first algorithm that I'm going to kind of dive more deeply into is going to tackle this question. How do we learn without a reward function by proposing and reaching goals? And as I mentioned at the beginning, this lecture is really intended more to discuss sort of cutting edge research topics and maybe provide a slightly different perspective for thinking about exploration. So I won't actually discuss the algorithm in sort of enough detail to implement it, but hopefully enough detail for you to kind of understand the main ideas. But I will have references to papers at the bottom, and if you want to get all the details, then I would encourage you to read those papers. But think of this more as a way to get a perspective on how we can approach this unsupervised exploration problem mathematically, less as a specific tutorial about a particular method that you actually should be using. All right, so the example scenario, again, that we're dealing with is this setting where you have a robot, you put it in your kitchen, it's supposed to spend the day practicing various skills, and then in the evening when you come home, you're going to give it a task, and perhaps you will ask it to do the dishes, and should somehow utilize the experience that it acquired to perform that task. Now, one fairly mundane thing that we have to figure out for this before we can even get started is how we're going to actually propose, how we're actually going to command goals to the robot once the learning is finished. So if you want sort of a real world analogy, maybe you can think of it like this. Maybe you're going to show the agent an image of the situation that you would like it to reach. In RL parlance, this would amount to giving it the observation or the state that constitutes the goal for the task. So what you would like is you would like to somehow have the agent learn something that enables it to accomplish whatever goal you give it. And the goal will be specified by a state. If we're talking about images, maybe it's an image of the desired outcome. This is not necessarily the best way to communicate with autonomous agents, but it just allows us to nail down something very concrete. The problem will be, given a state, the agent should reach that state. And then the unsupervised learning phase should train up a policy that would allow the agent to reach whatever state you would care to command it. Now, as a technical detail, we need some mechanism for comparing different states. If those states are very complex, like images, just like we saw in the exploration lecture on Monday, we need some notion of similarity between those states, because in general, in high-dimensional or continuous spaces, every state will be unique. So there are many ways to deal with this problem, but the way that we'll deal with it for now is we'll say, well, let's just train some kind of generative model. The particular generative model I'll use as a working example is something called a variational autoencoder, which we'll cover a few weeks from now. But there are many other choices. And we'll just assume that this generative model has some latent variable representation of your image. So if your image is X, you can also think of it as a state S, then your latent variable model will construct some latent variable representation of that state, which I'm going to denote as Z. So Z would be sort of a compact vector that describes what's going on in the scene, and we'll assume that that vector is, at least somewhat well behaved, meaning that functionally similar states will lie close together in that latent space. But there are many ways to get this effect. All right. And then, of course, the main thing that we're concerned with is we would like our agent to basically have this unsupervised training phase where before we even specify any goals that it should accomplish, it can sort of imagine its own goals, propose those goals to itself, attempt to reach them, and as a result acquire a goal-reaching policy without any manual supervision, without any reward supervision. So intuitively what it's going to be doing is it's going to be using this latent space to propose potential Z vectors that it could try to treat as goals, attempt to reach those goals, and as a result improve its policy. Okay, so let's try to sketch out what such an algorithm might look like. We're going to have our variational autoencoder as our generative model. So that has a distribution X given Z, which is a distribution over images given latent codes. You can also think of it as S given Z. So I'm going to use X here, but S means the same thing. And then we have our latent variable distribution P of Z. And when you train a variational autoencoder, as we'll learn a few weeks from now, you also need an inference network that maps back to Z's from states. So if you have a generative model like this, one of the ways you could propose a goal is you could just sample it from the model. So you could sample your latent variable from the latent variable prior, so sample zg from p of z, and then reconstruct the corresponding image by sampling xg from p theta xg given zg. So that'll give you an imagined image. And again, you don't have to do this with VAEs. Any kind of generative model would work, something that can propose a goal. And then you could attempt to reach that goal using a policy. So your policy now would be a conditional policy. So it would be a distribution of our actions given the current image x and given the goal xg. And when you attempt to reach the goal using this policy, the policy may or may not succeed. So let's say that it reaches some state, and we'll call that state x bar. Ideally, we would like x bar to be equal to xg, but in general, it might not be. In fact, xg might not even be a real image. It may be impossible to reach. So you'll get some other image, x bar. And in the process of running that policy, you'll of course collect data, which you can use to update your policy, maybe using something like a Q-learning algorithm, like what you're doing for homework 3. And you can also use that data to update your generative model. So if in the course of attempting to reach that goal, you saw some other images that you hadn't seen before, incorporating that data to update your generative model might give you a better generative model that can propose more interesting goals. And then you can repeat this process. So this is a basic sketch of an algorithm that utilizes a goal proposal mechanism, an unsupervised goal proposal mechanism, and a goal condition policy, and the interaction of these two things leads it to propose goals and then attempt to reach them. Okay, but there's a little bit of a problem with this recipe, because the generative model is being trained on the data that you've seen. So it's going to generate data that looks very much like the data that you've seen, which means that if your agent figures out how to do one very specific thing, maybe it figures out how to pick up a mug, now it has lots of data of picking up that mug, and when it generates additional images, additional goals, it'll generate lots more data of picking up that same mug, and might not bother with other things. So this is where we can bring in some ideas related to what we covered in the lecture on Monday, some of these exploration ideas. Let's imagine that we have this 2D navigation scenario. So the little circles represent states that you visited. Intuitively, what you would like to do is you would like to take this data set and modify it, skew it some way to upweight the rarely seen states. Very much like the novelty-seeking exploration that we discussed on Monday. And if you can do this, if you can upweight the rarely seen states before fitting your generative model, then when you fit your generative model, it should assign higher probability to the tails of this distribution, so that when you propose new goals, it'll sort of broaden it out and visit more states there on the fringes, and hopefully expand its repertoire of states that it can reach. So this is the intuition behind what we want to make such an algorithm really work. So how do we do this? Well, the idea is that we're going to modify step 4. Instead of blindly using all the data we've collected to fit our generative model, we're going to actually weight that data. So that's basically what this step will be. So the standard way to fit our generative model is basically maximum likelihood estimation. Find the generative model that maximizes the expected log probability of the states that you actually reached, which I'm denoting here with x bar. Instead, you could imagine having a weighted maximum likelihood learning procedure, where you train your generative model to assign high likelihood to the states that you've seen, x bar, but weighted by some weighting function, w of x bar. And intuitively, you would like that weighting function to upweight those states or those images that have been seen rarely. What do we have at our disposal that can tell us how rarely something has been seen? Well, we're using a generative model to propose these goals, and a generative model should be able to give us a density score, just like when we learned about counts and pseudo-counts. So what we can do is we can assign a weight based on the probability density that our current model p theta assigns to that state x. So we'll set the weight to be p theta of x bar raised to some power alpha, where alpha is a negative number. So this will essentially be 1 over p theta of x bar to some positive power, or equivalently p theta of x bar to some negative power. And one of the things we can prove, I'm not going to go through the proof for this, but the proof is in these papers. It's possible to prove that if you use a negative exponent, then the entropy of p theta of x will increase, meaning that each time you go around this loop, you will be proposing broader and broader goals. And if your entropy always increases, that means that you eventually converge to the maximum entropy distribution, which would be a uniform distribution over possible valid states. Now, a uniform distribution over valid states is not the same as a uniform distribution over x. So x might represent an image. Totally random images, just kind of static, might not actually be valid states. So what you should be looking for is a uniform distribution over valid states, a uniform distribution over valid images. Okay, now looking at this equation, one thing that might jump out at you is that this looks an awful lot like what we saw when we had pseudo-counts and count-based exploration. So if you remember, in count-based exploration, our bonuses had this form like 1 over n of s, or the square root of 1 over n of s. In general, they were of the form n of s raised to some negative power. Negative 1/2 if you have 1 over square root, or negative 1 if you have 1 over n. So this looks an awful lot like that. By raising the p theta of x bar to some negative power, we're actually doing something that greatly resembles this count-based exploration, except instead of using it as a reward, we're using it to train our goal proposal mechanism to propose diverse goals. All right, so the main change we're going to make is we're going to fit our generative model with this weighting scheme, where the weight is the previous density for that state raised to some negative exponent. Now, one question we could ask is, well, what's the overall objective of this entire procedure? It seems like we laid out a recipe, but in machine learning, we like to think of algorithms as optimizing objectives. So what is the objective for this algorithm? Well, I mentioned that the entropy of the goal distribution will increase every step around this loop, which means that one of the things we're doing is we're maximizing the entropy of the goal distribution. That's good because we want good coverage. We want to cover many, many different goals. So the goals get higher entropy due to this skew fit procedure. What does the RL part do? Well, your policy, which you can also write as pi of a given s comma g, so it's probability of action given current state and given goal. Your policy is trying to reach the goal g, which means that as the policy gets better, the final state, which I'll denote as s here, is going to get closer and closer to g. So that means that the probability of g given your final state becomes more and more deterministic. Essentially, if your policy is very good, you could pose this question. Given the final state s that the policy reached, what is the goal g that it was trying to reach? If the policy is very good, you could just say, well, the goal was probably the thing that it actually reached. Because it's a good policy, it's going to reach its goal. So that means that the better the policy is, the easier it is to predict g from s, which means that the entropy of p of g given s is lower. So that means that you're also minimizing the conditional entropy of g given s. And now when we look at this equation, something should jump out at us. That if we are maximizing h of g minus h of g given s, that means that we are maximizing the mutual information between s and g. And maximizing the mutual information between s and g leads to good exploration, because we're maximizing the entropy over goals, so we have coverage of all possible goals, and effective goal reaching because we're minimizing the entropy of the goal given the state. So that's another way that this concept of mutual information leads to an elegant and very simple objective that quantifies exploration performance. Essentially, in this case, the mutual information between states and goals quantifies how effectively we can reach the most diverse possible set of goals. All right, now for a quick robot video. This was an actual research paper that we did a few years back, and what we did with this kind of objective is we put the robot in front of a door. So that's that hook-shaped thing. That's the gripper for the robot. but we didn't tell it that it needs to open the door. It was just supposed to figure this out on its own. And in the top row, you can see the goals that it's suggesting to itself, the actual images that it's generating. And in the bottom row, you can see the behavior. And at 0 hours, it's not really doing very much. It's kind of wiggling around in front of the door. 10 hours in, it tends to touch the door handle and occasionally gets the door open. And after 25 hours, it pretty reliably messes with the door and opens it to all different angles. And when the system is fully trained, then you could give it an image of the door open to a different angle, and it will successfully open it to that angle.